All right. Good afternoon. Thank you all for coming. This is the first live event in 2 years, so welcome. I understand there's a ball afterwards, which is also important, so please stick around. This meeting is really to collaborate and connect, or connect and collaborate. We have esteemed speakers, Hamid from our department or the faculty of artificial intelligence. Welcome in a clinical setting, welcome in the hospital. Gloria from ENT, and Ritch from general surgery. So it's a whole spectrum of speakers, and that's what Dash is all about. It's about collaborating and connecting and cross-pollination. So this will be our schedule today. Please feel free to raise discussion at any time. So if you have any questions, raise your hand, and I will walk around with this microphone. And then we have an hour of drinks afterwards. And my name is Doornberg. I'm an orthopedic trauma surgeon, so I put together broken bones. I did 2 cases this morning. That's my trade, and I'm part of the Dash group 1 day a week as a for clinical input, so to say. So it's a great pleasure to work with all these very smart people. So what we aim to achieve is to say it's not so humble, but let's see if we can be a front runner in Holland, maybe even internationally, when it comes to data-driven healthcare. So, for example, in my case, patient-specific predictions based on machine learning. Why? Because we think that if you have a patient-specific individualized care, treatment improves. And if you want to state it, it's a data-driven innovation contributes to our goal of building a future of health. So potentially we are on the frontier here in Groningen, and our new decaan, Veronice, will certainly contribute in this direction, I'm sure. So what can you get out of us, out of the Dash group? These are the pillars. So clinical applications of AI, that's the field I'm interested in, to see if we can help patients with data-driven care. Machine learning, that's Peter van Ooyen, not here today, but that's very imaging-based clinical cohort data. Rosemarijn, she's from the radiology department, and e-health is Esther. And these are, so to say, the clinical input into the Dash community of all smart computer scientists and support team. So what do? We collaborate. That's basically our aim. We try to collaborate, try to put people together in the same room, which we established today, and see if we can cross-pollinate on, for example, in general surgery, you guys are doing image fusing in theater. In spine surgery, our field, that will be something we could copy-paste potentially. So that's what it's all about. There's expertise at some point, and then another point in the hospital, we try to see if we can help each other. So project support, education, part of today, and of course help with the funding opportunities. If you apply in a consortium, you're stronger than if you apply on your own. And that comes to fruition in an AI think tank. In the UMCG, we have an AI think tank. We come together once every 3 months, and we basically advise our board of advisors, or actually our board, to watch what direction they should steer when it comes to data-driven healthcare. Peter van Ooyen has a machine learning lab. We have an ELSA lab, very important, ethics in AI, IT lab, and then again, communities. Let's kick off. Gloria, this is yours. Please, the floor is yours. Thanks so much. I'm very curious to see what the robots will do, and also the content of your speech when it comes to auditory robotics for research applications. Do you want this pointer? Good question. Yeah.
Thank you. Yeah, maybe
Please go ahead.
That one. Right. We're a bit early, so I think that gives us 5 minutes. Not that I'm going to take more 5 minutes, but we shall see. If you want to, please stay by the end of this. Of these 3 talks, we will show a demo with 2 robots. That demo will take about 5 minutes. I'm not going to do it now unless you really want me to. So let's start then. Welcome, everyone. I'm here to introduce to you our research group, Aurora, and our main line of research, which is human-robot interaction. So, first of all, my name is Gloria Araiza. I studied biomedical engineering in Mexico, and then I moved to the UK, to Bristol, for both my master's and my PhD in robotics and autonomous systems. I've always been interested in developing robotic applications, not necessarily clinical applications, but yes, into robotics in general. So for my bachelor's, I worked on this was a mobile intelligence system for guiding visually impaired. So you can see that it looks like a cane with wheels. That's exactly what it was. And it could take you from point A to B, avoiding obstacles we were using AI back then. Then for my master's, I was working in a bio-inspired control algorithm for this 2-link robotic arm. And then for my PhD, I moved to transcutaneous electrical nerve stimulation for haptics, which means in normal English, it means I was trying to explore if we could produce different tactile sensations using voltage. So with this tiny electrode, you would just put your finger on it and I would give you electroshocks to see if you could feel different things. So before I move on, I would like to get to know my audience, just to tune my second and third slides accordingly. So can you please raise your hand if you are doing a bachelor's degree? May I ask in what? Oh, all of you, okay. Do we have any master's students in? Okay, PhD students? Okay, in what, sorry? Somebody? Okay, cool. Do we have any clinical staff? Medical staff? Okay, thank you. Any engineers? Thank you. And who is into technology, generally speaking? Oh, so not everyone? Okay. That's all right, interesting. Okay, thank you. So then please help me out for this. What do you guys think a robot is? Can I have somebody from bachelor's just giving a quick description of what a robot is? What is a robot? All right. Yeah. Okay. What about somebody from masters? Or PhDs? What is a robot? Yeah. Okay. Yeah, right. What about the medical staff? What is a robot? Okay. What about the people that are doing some business or marketing? What is a robot? Non-human actor. Okay. Good definition. Not always, but yeah, okay. Let's go through some examples and then you guys tell me if you think, well, first if you know what this is and then if you think this is a robot or not. Do you know what this is? Yes. Is it a robot? How about that one? What is it? Yeah. Is it a robot? Semi. Okay. Interesting. How about that one? Do you know that one? Does anybody know what it is? It's a Lego Mindstorm. So you build it with Legos, and then it has here is a console that you program. Is it a robot? Or is it a toy? Or is it a robot toy? What about that one? And it's a robot. Okay. How about that one? Have you seen this before? That one can do some parkour and some fancy dancing. What about that one? Have you seen it? Yes. What is it? The name is Baxter, and it is used in industry. But yes, it can do fancy things with the arms and with the facial expressions. What about that one? Luke, what is it? What does it do? But it swims very nicely. And that one? Have you seen that one? What is it, Jenny? Yes. Oh, but you can feed it. You can feed it, and it blinks and it moves, and it's very cute. It doesn't have to, but it does it. So is it a robot? Let's just think about what a robot is. Now I'm going to move on to what a robot can do in the UMCG specifically. And I think this question can be addressed at different levels. I think, the first of all is for the researchers, what can it do? And I don't want to talk just yet about what we do in our specific group or department, but generally, for example, you could potentially use a robot for handling chemicals or tissues or performing certain tasks. Yes, maybe to save some money, but also in environments where your human might be at risk. So if you're handling like dangerous substances, you might want a robot to do that with very high accuracy. Also for the clinical staff, not mentioning the surgical robots, I would think that we could have robots transporting medicines or other medical equipment to specific areas within the hospital. For the patients, of course, you could have surgical robots. You can also have rehabilitation robots, like exoskeletons, to help out people that have had, for example, strokes. For the patients as well, you can have soft robots or some other kind that there's one capsule, for example, that moves throughout your digestive system, and it has a camera, so it is recording the whole thing. That's also really cool. In case you didn't know. But you also have what we call social robots. And that you can use as companions or, for example, coaches, or if you need the person to do something specific, to be taught something, then you can use a robot. And it can be telling you when to take a medication, for example, if you need to be stretching, if you need to do some sort of physical activity, the robot can not only tell you how to do it or when to do it, but show you and do it with you. So it becomes, again, a social companion. And then for visitors, probably you have seen this in movies, or if you go to Amsterdam or to Singapore, then you have this in restaurants. The robots bringing the food. You could potentially have... Oh, it's in Groningen as well. Okay, that's news. Thank you. You could potentially also have that. You could have them guiding people in the hospital or giving you extra information and making their experience, a more positive thing to remember than just something that is not very nicely associated to hospitals. And now moving on to what we do specifically in our research group. We are called Aurora, which means Auditory Robotics for Research Applications. We started this group 2 years ago at the Dennis Bashkent Speech Perception Lab. Dennis is right there. She's the boss. She's the main woman. And we are part of the ENT Orca and department. And what we do is we have these two little things. The red one is called Sam. The other one is called Robin. Yes. Bit slow, but thank you. So we use both of them to do three main things. One is introducing and explaining a test. Then we also run the test, and then we also score the test. And I'm talking about, of course, auditory tests or auditory tasks, because we're part of the EN team. And we do speech perception. We use them for both normal hearing and hard of hearing populations, ranging from children to adults, potentially as well elderly adults. And we base everything in human-robot interaction. But one could ask, why a robot? Well, in the robotics community, it is known that for repetitive tasks, sometimes when you introduce a robot to the equation, it produces better performance because the user is more engaged. Why? Well, it can be due to a novelty effect coming from, well, it's a robot, and probably you've never seen one, nor interacting with one in that way. But also because you can give them some social features, such as blinking, or if they move. And it doesn't really have to be a humanoid like that. If we go back to the previous slide, like a Roomba, when it is bumping on your foot, that is also interacting with you in a way. And the way that it behaves, it might give you some sort of social feature that you might feel it feels like a dog, or something that is not just a machine. So that's why we use robots, because auditory tasks, they tend to be repetitive, and people, especially children, for example, they might struggle completing a test. So our hypothesis is if we bring the robot, it might be a nicer experience, more engaged, and potentially better performances. But what exactly is human-robot interaction? Well, as the name says, is the study of the interaction between a human and an embodied machine, which is a definition of a robot, by the way. Well, it is an interdisciplinary field covering all of these areas and potentially even more areas. And as such, then it comes with different challenges from the social and physical design, for example, point of view, but also not only from only robotics, but from technology in general. So again, please think about how you guys or everyone here or in the world really, how we interact with technology and robots, and to what extent you would categorize that as a social interaction, because the main aim of human-robot interaction is looking at the robot as a social entity or a social agent. So more specifically, what we do in Aurora is developing clinical applications based on human-robot interaction. And we do everything from the designing of the interaction to the implementation of the robot, to the evaluation of the HRI or human-robot interaction. And how we evaluate that, well, we use basically three approaches. First, we'll look at the task outcome, meaning the scores of the auditory tests, as in how well are humans performing when using the robot. Then we look at the robot's performance, meaning all the sensors and actuators. Are the buttons, for example, working as we are programming them? Are the algorithms working as well? The cameras, the speech recognition, but also actuators. So in this case, we're looking at the motors or the speakers, for example. And then we're looking at the human's perception of the robot. And how we evaluate that specifically comes down to questionnaires and behavioral coding. This is what we normally use. There are other ways, of course, but this is what we focus right now at. And we might also include informal interviews. It really depends on the design of each of our experiments or studies and well, what population we are approaching. So for example, if you have children, then of course, probably a questionnaire is not going to be a great idea. You might want to have informal interviews or just behavioral coding. So as I said, we are based on, well, we work with these three main ideas. First one is checking if working with robots can result in a more engaging task or more engaging experience than when using the normal interface. Again, I'm talking about our specific applications, so auditory tests. And the normal testing interface or the default testing interface is usually either a computer or a tablet or a speaker. Then we're interested in comparing the scores that we get when our humans are performing this auditory task with the robot to when they are using the default testing interface, which is again the computer, the tablet, or the speaker. And by comparing this, then we are hoping to gain the trust and will of our clinicians to use our robots more often. Because if we can prove to them that it is equivalent to the tool that they already use, then it might be easier for them to adapt to this new technology. And that brings me to the third one, which is we want the robots to be available for our medical staff, to be available as an alternative clinical evaluation tool, which can potentially be used for diagnosis or rehabilitation or whatever it is that they want, just as another thing that they have, like a plug and play kind of tool. We want to have this as a final product for them to use. And I should emphasize that we're never trying to take their place. We're trying to work with them, because we have seen so far that the best result we get is if we work together as a team. So we want to include them, and we never want to replace them with the robots. Just to wrap up, this is just a quick example of what we do, or how it looks like what we do. This is one of the interactions designed for children, in this case cochlear implanted children. After the test, the robot was saying well done and then giving them a fist bump or a box, which was very funny to see. Most of the children loved it. Some of them hated it, and some of them cried. Anyway, but in this side, you can see what behavioral coding looks like. So this is just one example of, this is a study comparing how our humans were behaving, as in looking at facial expressions and body language of our participants when interacting with the robot. This is in blue, the robot, and when interacting with the laptop in red, orange, coral, whatever color it is. Highlighting in yellow the specific features that we were taking into account to evaluate how positive their experience was. And this is the work of our PhD. Luke, say hi. Thank you. And just to finalize, this is our current work. What we do these days is we're trying to implement automatic speech recognition. Well, we have actually implemented it. We're just exploring the limitations of automatic speech recognition when using it for scoring of the tests, for automatically scoring the tests. So sometimes we will have the robot explaining the test and running it, but then we will have a human supervisor, in this case, mostly clinicians, scoring the test manually. Also probably due to the fact that they don't fully believe in the robot yet. But this is what I mean with, if we manage to get some good results and to share these results with them, then they might trust the robots more, and then we can work together in an easier way. And then offering natural conversation as well. That is, part of the agenda to make the robots more autonomous. So of course, that's always a nice thing to have something more intelligent for the interaction to feel more natural. And nowadays we're testing multiple populations, specifically hard of hearing children and hard of hearing adults, and potentially going into older adults, which might be challenging as well. Every population is challenging, but it's very interesting. And I must say that we're doing all of this with the lovely collaboration of Kentales and the University of Twente. So before I say thank you, basically the take-home message that I would like you guys to have is to think that, or to be aware of how close technology is now to us nowadays, how you can even have a robot at home and you didn't realize, or perhaps you do realize, but the level of interaction is already there. So might as well explore it to some to other degree, which is clinical applications, because there's a massive potential for robots in healthcare. Thank you.
Thanks so much, Gloria. I worked in Australia for 4 years, and we had a brand new, we had a brand new hospital. It was the most expensive building on the Southern Hemisphere. And we had robots taking food from the basement up to the patient wards. And the carts with food arrived empty because all residents and students thought it was some kind of room service. So when there's no human in the loop, it may be challenging, but the robot worked perfectly. Thank you so much. Any questions from the audience? Yes.
How do you want to include the empathic compartment into the robots for the interaction?
Empathetic, you mean?
Yes.
So empathy in the robot. There are multiple ways of doing it. One of them is mimicking how the human behaves. So of course you need to add some other layer of artificial intelligence in this case, and you can do it through vocal cues, visual cues, or a big thing that we do in human-robot interaction is Wizard of Oz, which means there's somebody behind the computer and everything is an illusion, but you don't know about it. That is mostly used as a proof of concept. So you could use that as a first step, just to test whatever approach you want to test, and then see if it is actually coming across as something more empathetic. And then if it is, then you add the artificial intelligence, the corresponding neural networks behind it, and then hopefully it would work. But you can also do it just by gestures, or like using the same words that your human is using the same pauses. So it has to do with everything. Again, vocal cues or nonverbal cues as well. But you also get that with like tracking your gaze, just by something looking at you and blinking. And if you move, then it moves with you. Then you feel much more connected.
You said them and they about clinical staff a few times.
Yes. Hello.
Are people scared that that robots take over the jobs? Because I would love it if some task would be taken over. Would be great, I think.
I don't think they are scared. I think they're very protective of the patients, which I understand. So of course, that's also a big thing that we should take into account, that you cannot afford to have a robot running freely, so to speak. It has to be safe. So I think, especially because our clinicians are very fond of, for example, cochlear implanted children, it took a while to convince them to give us access and try to show them that we can be helpful. But yeah, I think it also has to do with probably a generation gap, and they're not very used to technology.
Yeah, it makes sense when it comes to patients. Yeah. Any other questions from the audience? Well, thank you so much, Gloria.
Thank you.
If you come up with any questions, we have a borrel and a demonstration at the end on your end. I think Hamid, you're next. Is that right? So Hamid is from outside the hospital. Thank you so much for coming. I think you will get a lot of questions about collaborations after your talk. So thank you.
I hope so. So, okay, good afternoon, everybody. My name is Hamidreza Kasaei. I'm an assistant professor at the Department of Artificial Intelligence, doing robotics for quite a lot of years, more than 15 years. And today I'm going to talk about adaptive assistive robotic system to improve the life of patient or user actually with kind of disability. Nearly 190 million people in the world live with some sort of motor impairment that can happen due to a genetic disorder such as SMA, ataxia, muscular dystrophy, or atrophy, or it can happen because of a life event such as a stroke, accident, or injury. What we do actually for these people is that we provide them actually an electric wheelchair equipped with a robotic arm and also a joystick interface that the user can use that interface to control the wheelchair as well as the robotic arm to do the daily life task. In particular for these people, object manipulation is a high priority task. And you may ask why actually object manipulation is important for them. The underlying reason is that if they can be able actually to manipulate different objects in different situations, they can be more independent. They can do their daily life. They can, for example, go to a supermarket, do shopping. They can go to a coffee shop, order a nice hot chocolate and enjoy it. They can post their envelope. They can do their daily activity and social interaction, eating, drinking, and therefore they will be actually much more happier than before. And also they will be involved in the community and so on. However, the current technology are very limited. If you pay attention actually to how difficult it is to control a robotic arm opening a fridge and pick up an item from a crowded fridge, as you see here. So the patient actually should several times change the mode of the wheelchair and also the robotic arm in order to be able to control it autonomously and correctly. Therefore, this process actually is difficult and requires fine motor control, which this fine motor control actually is not necessarily valid for every this type of patient. From the other perspective, manually controlling such a robotic arm is slow and require careful movement, which for some type of patient also, especially those that experience brain surgery or a stroke, it might be actually not possible. This process here is slow, and the user actually should carefully move the robotic arm in order to do the task. For example, here the task is like serve a beer, and the user very carefully move the robotic arm in order to grasp the bottle, pick it up, and rotate it in order to pour the beer into the glass, and after that try to find a free place in order to place the bottle and then drink the beer. The main question here is that can we develop a cognitive robotic system to overcome these limitations, to have a robot that can work like more autonomously and faster? In my research, I tried to address this problem through a lens of object perception and object manipulation. For example, if we have, I'm not sure this laser is working or not. So if you have a camera there, so the robot can perceive the environment, and the user can just say, hey robot, this is a mark, can you grasp it? And the robot can do that autonomously. So here you can see that the robot detects the mark object and can go to a pre-grasp area automatically without any manual control. Even later, when I move the object, the robot can also track the pose of the object and try to adjust its behavior and its position and move to the pre-grasp area for the mark object. So this type of technology, to interact with the user and also for the environment, the robot needs to know which kind of object exists in the scene, where they are, and how to grasp and manipulate this object in different situations. Therefore, object perception and object manipulation are two key functionality for this type of robot that should be tightly coupled together in order to perform a task in a right time in an appropriate manner. Although so far actually we have a lot of development in robotics, computer vision, and machine learning, we still do not see such a robot in our daily life or in our society. What is the main reason for that? In my opinion, the main reason is that in most of the robotic system, the training and testing are two separate phases. And therefore, the performance of the robot strongly depends to the quality and quantity of the training data. Furthermore, the knowledge of the robot will be fixed after the training stage. And if we want to change something else or introduce a new object to the robot, someone actually, especially an expert, should come by, collect a lot of data, retrain the robot again and again, which is time-consuming, expensive, and complex procedure. Therefore, this type of approach limits the applicability of robotics in our society. It should be noted that this type of training and testing works very well actually for factory-like environment where everything is predefined, such as a logistics center, car manufacturing, that you know in advance at which time which object will be at which position. It can also be used for disinfecting facility where no one actually is running around or moving around and everything actually is predefined or stable and static. For a couple of seconds, have a look at these pictures. These are the instances of human-like or human-centric environment. In such a domain, it is not really feasible to assume that one can pre-program the robot in advance. because the robot usually actually faced with a new object, new task, and new environment. And it also depends to the user preference. So it is not possible to completely pre-program the robot. In my research, I tried to achieve a scientific breakthrough to enable the robot to learn new tasks in an open-ended fashion, mainly based on interaction, imagination, and imitation. So in my research, open-ended means that the training data are coming in an online manner, and they are not predefined. For example, the user can point to the object and teach the robot that this is a mark and you can grasp it this way. So this teaching actually can be through verbal, language, or kinesthetic. And later the robot, I hope that this is working, yeah. Later the robot actually should perform the task in the same environment to show that it learns actually that task specifically. And also it should be able to generalize its knowledge to new domain and new task. For example, if the robot learn how to serve a juice, it should be able actually to serve a beer, because they are like semantically similar. Let me explain it better using a cartoon example. Assume that we have a service robot that is able to do a clear table task. For this task, the robot actually should remove all non-decorative objects from the table, which in this example are bottle, bowl, and plate, and also put the decorative object, which is vase, into a predefined area. In this task, the robot knows about bottle and bowl, but it doesn't have any information about plate. So it removed the bottle and bowl from the table and then asked the user, what is this object and how should I grasp and manipulate it? A human user actually come by, which is a non-expert user, and try to teach the robot, this is a plate, a non-decorative object, and you can grasp it this way. Do you want to try it? So since I'm here, I can confirm your behavior to address the safety problem. Then the robot actually tried to grasp the object, put it into several positions in order to capture like several viewpoints of the object, and also learn how to grasp it in different situations. And after that says that I learned this concept, and if I later face with this object, I can confidently recognize it and manipulate it. So this is an idea of open-ended learning. So we do not need to program the robot again and again, and a non-expert human user can teach the robot new task, new object, and whatever it wants. Whenever actually we move to the assistive robotics, in addition to open-ended learning, we need adaptability, trustworthy, and capability. It means that the robot should be able actually to adapt to new task, new object, and new domain based on the preference of the user. And also it should be able actually to show some sort of explainability to capture the trust of the user. In particular, if the user doesn't trust the robot, it never use it, regardless how capable the robot is. So upon request, the robot should be able to explain what it will be actually perform to achieve a given task. The robot should also be capable to accomplish a task in an appropriate manner and in real time, because we don't want to have like a very slow robot that you ask him to serve me a drink and it takes like 1 hour to prepare the drink. So this is our robot Luca in our artificial intelligence department. It has an RGBD camera, and a speaker and microphone array on his head, a dual arm manipulator, which each arm has 6 degrees of freedom, and the payload of each arm is like 5 kilograms. So one of the arm has an anthropomorphic hand, as you can see here, with 5 fingers, and the other actually has a 2-finger hand or gripper. So in human-centric environment, this type of robot actually faced with like different type of object, and each object has its own functionality. For example, a non-expert human user can teach the robot through demonstration that you can actually grasp this object in this way, and using like few demonstration, let's say 5 to 10 demonstration, the robot should be able actually to learn how to grasp and manipulate this object. And also it should be able to generalize the acquired knowledge to never seen before object or novel object. For example, how to grasp a headphone, a toy, flower, and so on. Let me show you an example how a server drink is using this type of robot and how robot can help us in various daily tasks. In this scenario, the robot doesn't have any information about this object, and this is what the robot can perceive through its camera. So it first recognizes all objects as an unknown, and then the user used this graphical user interface to teach the robot that this is, for example, cup, this is beer, this is a trash basket, and then instruct the robot to perform server drink task. There actually you can see the perception of the robot, and here you can see the action of the robot. So if you compare this performance with the performance that I show you at the beginning of this presentation, that the user manually controlled the robot, you can see how faster actually is this action is through autonomous behavior or autonomous control. In another task, the robot can be used for arranging a messy table. Here actually the robot uses again its perception system, which is an RGBD camera, and it is in front of a messy table, and it has to put the object into like two baskets. The objects that are in the right side should be placed in the right basket, and the objects that are in the left side should be placed in the left basket. Of course, in this scenario, several failures might happen, but the robot should be able actually to recover from its failure and try to grasp the object. If an object grasping failed, it should be able actually to grasp it from the other part of the object and try to place the object actually into the basket. So the user actually also changed the position of the object, but the robot adapt its behavior and try to grasp and remove the object and put them actually into the basket. So in addition to grasping and manipulation and learning about new object, as I mentioned, the robot should also show some sort of trustworthiness. Meaning that if the user actually asks the robot, how would you do server juice task, it should be able actually to explain it either verbally, through a language, or based on a simulation. Here we develop an accurate simulation environment for the robot that before the execution, it can show the process to the user. And if the user agree with the process, it can confirm the behavior, and the robot will start to execute it on the real robot. This type of simulation environment is also good for evaluating the robot in an extensive manner, and also teach the robot in advance about different tasks whenever the user have time and are in the mood that would like actually to work with the robot. So in human-centric environment, it is not, the environment actually is not static, and it is mainly actually dynamic. And the robot should be able to adapt its behavior to the environment. So for example, here the task was put the milk box into the red basket. So the robot perceived the environment, as you can see here, and the user actually pushed an obstacle into the trajectory of the robot, and the robot is able actually to adapt it. So not only actually we push an obstacle to the trajectory of the robot, but also we change the position of the goal. As you can see here, actually the robot is able actually to adapt its behavior. So as one of future work that I really would like to pursue is that can we use such a robotic system for engaging children with developmental delay, such as autism, to do like more activity. So in this scenario, actually, we ask the robot actually to throw the object instead of pick and place. It tries to throw the object into the basket. If it can ask a children actually do the same, that would be also, I think, great, and it will help them to improve the motor control. As a conclusion, I would say that my research is central to many health-related applications, ranging from assistive robot to managing environment and logistics. It can be used for entertaining children. It can be used for ease stress on nurses and patients, and so on. I would like to thank at the end of my presentation my student and actually my colleagues who helped me a lot to develop this line of research at the Department of Artificial Intelligence. And if you have any question, I would love to answer it if I can.
Thank you so much. Really cool. Any questions from the audience? Many questions. Good.
Oh,
Thanks. I was wondering, how will you be giving those commands to the robot? So will it be, for example, the robot is in front of a table and he sees, oh, I could clear this table, I could serve a juice, here are the options, pick one of the options? Because I guess a lot of the people using this would also have some kind of speech impairment and would not be able to, verbally interact.
exactly. So for different actually user, we try to make different user interface in particular. Those patients that actually can talk to the robot, we will use actually like speech recognition, in particular through large language modeling. That nowadays is like one of the hot topics. But for those that are not able, we actually develop a graphical user interface that if you can see here, actually, the user actually use this graphical menu to teach the robot that graphical menu, right? The colorful one. So to teach the robot that, for example, object number 1 is a mark, and the robot will conceptualize that. In the case of the task execution, it can also say that, please give me a mark, for example, and this kind of thing. We also actually make it in a way that a non-expert human can add more and more functionality to it.
Have you found a way to get this to patients or to the market already?
I recently actually submitted a research proposal with one of the company in Netherlands called Focal Meditech. They are actually like main expertise on this type of devices, and we are really working together hard to make it possible.
Okay, thank you.
You said that the open-ended, let's say, training is more applicable to human environments, a mess in a room. Is that open-ended training now also in car manufacturing, or is it still the classic training annotation of the robots?
In my opinion, in car manufacturing and also in this autonomous driving area, if your question is in that direction, everything can also be predictable. So we have like pedestrian, we have different cars, it is like much more structured than human-centric environment. The main thing actually in healthcare is that different users have different preference and different need. And it is not really possible to make it like very specific for each user. So we try to let the user actually to develop what they want.
Yes. Or maybe throw, yeah.
Yeah.
Thank you for your talk. So you said that one of the robot needed a grasp demonstration. So if the user cannot grasp an object, how do you envision this kind of training to take place?
In particular, the idea is that even, of course, actually the user may be actually not able actually to show that demonstration, but another non-expert human user can do that for the robot, right? So for example, one of the family member can do that, and it improves over time. The good thing actually with this kind of learning is that if you, for example, teach the robot how to grasp an spray, it may be actually be able to generalize this knowledge to grasp another object with similar functionality. So, yeah.
It's a long distance throw. If you can make it over there, we'll ask another question. So do you envision a robot in the ward helping nurses and staff without a specific assignment, and then seeing a bed that should be made and trash on the floor, and doing that all that stuff automatically? Is that something you can start organizing from this tabletop perspective?
It depends actually. So there are a good line of research actually on this topic that let the robot actually do imagination similar to human. Consider human, whenever we ask them actually to do something, we start thinking about that. We start imagine, if I do this task or in this action, and later actually I do that action, I can accomplish the task. So we will try actually to let the robot do similar thing. So they can think in simulation first, and whenever actually they have a concrete plan, they will start to execute it on a real world scenario.
Cool. Yeah, go ahead.
I was wondering about like giving tasks. Is it also possible to would it be possible in the future to give tasks directly from someone's brain if he's not able to speak or move well enough to give tasks?
I think it should be possible. In the Department of Artificial Intelligence, one part actually is about like cognitive modeling, and they actually they are working on eye tracking and understanding the signal of the brain using EEG and this kind of thing. By encoding those signals, it should be actually possible to provide some sort of user interface that later the user actually do whatever they want.
Thank you.
There are robotic arms that are via neurostimulation or how is it? Controlled. Okay. Yeah. Any other questions?
Yeah, so thanks. So I had a question about the explainability that you mentioned. So the kind of explainability seems very minimal. So I thought, so as I understood it, you explain to the user what is going to happen.
Mhm.
So I thought would perhaps be even more informative if you could also tell something about the reasons that something is going to happen. Then because it might
Exactly.
make it more easy to
To understand it, maybe.
to change it also if something doesn't work as expected. So is that something that's you're planning to add or is already there?
You know, explainability also is like a very active line of research, and of course it is very important for this type of application, because if the robot actually is not able to explain how it comes to that conclusion given an instruction, so the user actually will not use it anymore after a while. Therefore, the robot actually should be able not only actually through this digital twin simulation to explain what is going on, but it can actually explain it through verbal communication or textual communication, explain how it comes to that conclusion for a given task.
Okay, so this already does more
Exactly.
than merely explain
Visually,
what it's going
exactly.
to do. It can also explain I do this because it's a decorative object, and
Exactly.
you've told me that's supposed to go there. So these kind of things.
And the good thing actually with this kind of explainability is that if there is something in between wrong, the user is able actually to correct it.
Oh, nice.
So the robot actually can correct its plan just partially, not completely.
Okay, thanks.
But it's like, as I mentioned, it's like very active line of research, and you know.
Yeah.
We have a question
Halfway,
on the right.
perhaps.
Yeah, go for it. It's soft, so you can't hurt anybody.
Thank you, thank you. What happens when a failure happens? Can the robotics also correct his own failure?
Yes.
To take a
so
second
it
try,
depends
or-
actually to the failure. If the failure happen in a way that actually the robot like broke some part, so it is not maybe possible to recover from that failure. But if the failure is in like grasping and so, definitely actually the robot can recover from that. So in this demonstration you can see like several failure happen. So the robot tried to grasp the object but it couldn't, but later actually tried to grasp it from another part of the object. So for example,
But I noticed, for example, in this video clip, the last two objects were replaced in a new location to make it possible for the robot. But you see that one?
exactly.
Yes,
So,
but then
yeah.
it was later on put in a different location. So if you didn't do that, would the robots be able to try to
Yeah,
grasp it?
the
or-
purpose of this work actually was like object grasping in particular, but we have another work that we try to learn the synergy between grasping and pushing. So in particular, whenever an object is not graspable, the robot starts pushing the object and move it actually into the area that is graspable.
Thank you, thank you.
One last question and then we'll move on.
Thanks for the presentation. Do you also produce some kind of confidence for any task that they want to do? Because some tasks, I believe, like picking up the garbage is like mistake is affordable, but like feeding someone with a spoon, if the spoon goes to the eye or something, is not affordable. do you have a level of confidence for each task that they want to do?
In particular, yes, but we never actually try to like feed the patient actually using this type of like big hand, right? But usually actually the robots say that it represent the confidence based on the probability. So it says that 100% I can actually do this, or maybe I will fail, or I can do it like with 50%. Do you want me actually to do it, or do you want to see the explanation first or the demonstration in simulation first? And if you think that everything is working, I can execute it. But of course, actually for those that are like dangerous, so definitely we need like several level of safety check and this kind of thing.
Final question.
Would you dare to have coffee at your patient?
I believe that actually even a patient even the patient can control the robot by itself. They usually actually try to prevent this situation because it's like risky. Of course, actually always there is like, even if the robot can do the task like 100% in, there is like 1% actually for failure.
Thank you. It's a very inspiring talk and thought-provoking. Ritch, please come up. Thank you, Hamid. Thank you. And please stick around for the drinks. Ritch is part of the Esther Constant group, the robotic in surgery group. Floor is yours, mate.
Yeah, thank you. So, hello everyone. Thank you to Job and the organization for again a beautiful event and for providing us with the opportunity to introduce you to how we use the robots for colorectal cancer surgery. My name is Ritch Geitenbeek. I'm a MD PhD candidate here at the UMCG, and we're focusing mostly on robotic use in colorectal cancer, the surgical treatment. So I have no disclosures. Always start with a bit of a graphical image. It's good, keeps the entire crowd awake and focused. But there's a key thought behind it. The idea is that, like a couple decades ago, we used to think the larger the incision, the greater the surgeon. And fortunately, we now realize that often this is for the patient very disadvantageous. So we work towards more minimally invasive surgical techniques. In 1805, there was the Lichtleiter, which was first described. And since then, we've worked on developing laparoscopic surgery as the first minimally invasive technique, particularly for rectal cancer treatment, which is my field of expertise. We've seen that with laparoscopic surgery, there's faster recovery times, while still there's a good oncological safety that is comparable to open surgery. And nowadays, therefore, mostly laparoscopic surgery is being used for these patients. However, laparoscopic surgery by itself is still, it has some issues. It's technically very challenging, and that's because with laparoscopic surgery we have 2D vision. We're dependent on a person to move the camera for us, for the surgeon. And also, particularly, for instance, in rectal cancer, there's the pelvic area, which is a very narrow and confined space of the abdomen, which makes the maneuverability difficult. So the robot was developed. It may be a bit less fancy than we've already seen from our colleagues. It's the Da Vinci robot, which is now currently used a lot. It was first developed by the army with the idea that they wanted to be able to treat soldiers with life-threatening injuries in the field without having a surgeon present at that place. So the way it works, we have a surgeon console. You can see 2 surgeons, both sitting at the console. In the middle of the room, there's a sort of a monitor, and on the right, there's the robot, the robotic arms, which are often placed and sometimes replaced by the surgical assistants. When we started with the robot, it were 2 very rigid instruments, similar to laparoscopic surgery. So it was like you were trying to grasp a matchbox with 2 walking canes. It was very difficult. You had a very rigid instruments that were hard to control. Well, nowadays we've made significant progress, and we're able to perform more delicate surgery with the robot than we are able to do with our own hands or with the laparoscopic surgery. And also we've, for the robot, we have 3D vision. So this is the way the surgeon actually controls the robot. Like I said, there's many advantages of the robot. For instance, in laparoscopic surgery, there's the fulcrum effect, which is the effect of natural inversion. That means that when we sort of stick a rigid instrument in the patient, the point where it enters the patient forms as a sort of turning point, which means that if I move my hand to the right, the instrument in the patient goes to the left, which in the robot, left is left, right is right. So it adjusts for the fulcrum effect. The robot actually filters one's tremor that we all have in our hands, whereas with laparoscopic surgery it's enhanced because there's a long stick that you're moving around, and at the end you'll see more of the tremor. Ergonomically, we found that over 80% of surgeons that perform laparoscopic surgery for longer amounts of time, they develop back issues, whereas for the robotic surgery it's a relatively comfortable position to stay in for numerous hours. Then we also have the dual console. As you can see, there's often two consoles which allow surgeons to both look in 3D at the same view and to correct one another if needed, which is ideal for training young surgeons. Also, we think that the robot for colorectal cancer may be more future-proof compared to other platforms because it allows us to introduce telerobotics, targeted tracers, and fluorescence. As a new technique, of course, we had to look at if the robot was safe and what the costs of the robot were. And to explain that, I want to discuss with you some of the research we've done for the rectal cancer treatment. So, as the crowd is of different backgrounds, short background information on rectal cancer surgery. So the surgical technique we use is called a total mesorectal excision, which means that we remove the tumor as well as surrounding tissue because it reduces the chances of their remaining tumor cells, which will lead to local recurrence of the tumor. It was developed by Professor Hield. You can see a picture of him there. He's in his late 80s now, and he still visits every single colorectal cancer congress, which is really nice because he's no longer practicing, but he's a very interesting person. So the most important part is that we always aim for a complete resection. You want to remove the tumor as a whole to give your patient the best outcomes. That's all dependent on patient and tumor factors, but also on the surgeon's experience with the technique. Robotic surgery was introduced around 2010, so still there are many surgeons that are learning this technique. When looking at the safety, I see the red box has moved a bit. So the ROLAR trial was one of the largest trials that compared robotic rectal cancer surgery to laparoscopic surgery, and it found similar outcomes in terms of oncological safety. However, we found that we were comparing laparoscopic surgeons that had been using these techniques for 10, 15 years to robotic surgeons that were just performing their first surgeries with this. So we adjusted for the outcomes of this trial, and we found that it indeed had an effect on the postoperative outcomes. We also performed a systematic review, and from the limited literature that was available, we saw that also for robotic surgery, you need to perform between 30 and 70 procedures before you sort of reach your plateau, before you're confident and you have maximized your efficiency with the robotic surgery. Looking at these learning curves, we found that during the introduction period of the robotic surgery, there were similar intraoperative and postoperative complications, though for the first 30 procedures, the operative length was much longer for the robot, which makes it a more expensive technique. When looking at the long-term local recurrence rates, we found something that was, for us, very interesting. We found that even in the first 1 to 10 cases, there was already a local recurrence rate between 4 and 5%, which is relatively low and which we are not able to copy with other techniques during the learning phase. So, happened to be performed with another technique. These percentages for the first 10 cases may be around 10, 13%, which is significant. So this told us that the robot was safe even when you're studying and learning how to deal with it. Then we did a small retrospective cohort study in 8 centers, which was all for surgeons that were beyond their respective learning curves. And we found that if you compare laparoscopic to robotic surgery of surgeons that have done more than 50, 60, 70 procedures with the robot, they were able to provide equal postoperative outcomes as well as oncological safety. But particularly in the field of colorectal cancer, we found that with the robot, we were able to have a 20% lower stoma rate at 3 years following surgery. So, to put it differently, with laparoscopic surgery, you have a far larger chance of receiving a stoma for the rest of your life, which we think can be attributed to the better maneuverability that we obtain with the robot. And now we're looking into the long-term outcomes and the effect that this has on patients' quality of life in a Vantage trial, which is a study in 50 centers that we are currently performing in the Netherlands. We also looked at the costs of these techniques. We found that at 30 days post-operatively, the robot was between 2 and 2,500 euros more expensive compared to laparoscopic surgery. This is of course because the robot is more expensive to purchase, to maintain, and also the robotic instruments are still very expensive. Whereas for the long-term costs, we're now performing an analysis, and we think that for these patients, for instance, who do not receive a stoma, you might say stoma material cost is around 10 euros a day. So for every patient, you save between 3,500 euros for the rest of their life every year. So we think that in the long term, the robot might be more cost-effective than we now believe, which is a good thing because the robot's been busy these last 3 years. More and more centers have been using robotic surgery, and more procedures have been performed using the robot. So it's good that it might be safe and that it might be cost effective also. We are not yet at the point where we can let patients sort of safely interact with our robot. We still get the question often, so you'll be performing robotic surgery. Does that mean that you just flip a switch and then you go and drink a cup of coffee, and then when the surgery is done, the surgeon returns? We're not there yet. So we're still teaching the robot, and as it was already said, we can teach the robot how to do a lot of things, but as soon as one variable changes, often the whole plan goes to yeah, I'm being recorded. So we still need to teach the robot how to do things better. And as of now, we're still using the robot as a tool to find and explore the boundaries of minimally invasive surgery. And we've already been able to extend our success rates of surgery as we had with laparoscopic surgery. We're performing a lot of research, first of all, towards the diagnostics. So you might know in breast cancer, we often perform a sentinel node. So we look at the lymph nodes that the tumor is most likely to spread towards. And then if we see that these lymph nodes are attached or affected with tumor cells, then you can decide to remove a larger piece of tissue rather than just the tumor. On the other hand, if the lymph nodes are not affected, then you can often just removing the tumor is enough. We tried doing that in colorectal cancer for a number of years, but it was always difficult because of the fatty tissue that we have in our gut, which makes it very hard to identify lymph nodes. With the improved camera of the robotic system and new immunofluorescent markers, we think we might now be able to, for colon cancer, recognize these sentinel nodes. Here you see in our center with the robot, we've identified with the immunofluorescence one of the lymph nodes. We remove them, and then we want to have the pathologist check them. And if we're able to do this well enough, then we might, for colon cancer, at some point no longer have to remove 25 to 40 centimeters of bowel for even lower stage colon cancers. If the lymph nodes are safe, then perhaps we can be satisfied with just removing the tumor, which means no anastomosis and or stoma for patients. We're now performing this trial on the first 40 inhuman patients in our center. 3D pelvimetry. So one more project that we're working on is we know that the measurements within the pelvis can be predictive for surgical difficulty, which can be a predictor for intraoperative complications, blood loss, and the length of the surgery. However, it takes a lot of time for the radiologist to identify these points, so they don't do it regularly in clinical practice. So what we're doing is we've been training the robot with 100 scans, which we've annotated these points, and then we're validating how well the robot is able to recognize these points using a deep learning UNet framework. And up to a 2 millimeter error, the robot was able to identify these points for us, which could be a first step towards actually 3D pelvimetry automated for all patients in the Netherlands. And we're now working on assessing over 1,500 scans in which we want to develop a sort of 8-point system, and we want to see how well the robot is able to detect these points also. These are all bony landmarks because we're not that good in having the robot identify soft tissue yet. Then there's the AMIRA project, augmented minimally invasive robot-assisted total mesorectal excision. It's a mouthful. I practice that a lot. So this is one of our main projects that we're working on in the Netherlands or in Europe. Over 10,000 laparoscopic robot-assisted surgeries are performed annually. Some of these for colorectal cancer, of course. We've already discussed some advantages of the robot, but we still have a limited field of view, limited maneuverability, and we find that it's difficult that the robot is not able to provide the surgeon with haptic feedback. So what we're doing is we want to develop a decision support platform for the surgeon, which will help him during the surgery by, for instance, augmented visualization. So we want to use the preoperative MRI scans and transplant that image on the live surgical feed so that we're better able to recognize, for instance, the tumor, blood vessels, and nerves. We also want to develop endoscopes, which are shape sensing, to give us more information about the anatomy and where we're looking at in the pelvis, and force sensing to enable haptic feedback and to adjust for interaction forces. So of course, when the MRI is made, the patient is lying perfectly flat, and during surgery we often have to tilt them, sometimes a bit upside down, so then the organs tend to shift. So then the augmented visualization also moves places, and that's what we want to adjust for using the interaction forces analysis. And we do all that with a digital twin, which is made using AI and classical remodeling to sort of develop a digital virtual copy of the patient. This is just schematics. So what we do is, for all these MRI scans, we identify the most important structures. We have to still at the moment draw them in by hand. And then what we want to work towards is the augmented visualization. In this case, it was performed on a liver. And what we want to do is we want to provide the surgeon with all this extra information during surgery to sort of help him recognize what are vital structures that you don't want to accidentally nick into, and also to identify the tumor. And so what's the most difficult is we're working with a dynamic system which is constantly moving due to, for instance, the patient's breathing and our manipulation with our instruments. This is what we're working on for the colorectal cancer also. And then lastly, we're also working on phase detection. So this is in gallbladder resections. So what we did is we were sort of like assessing hundreds of operation videos, and we determine which phases of the surgery we're at. So this is the cutting of a vessel, this is the removal of the gallbladder. And then we teach it towards the robot using, again, deep learning. And we want the robot to be able to tell us what phase of the surgery are we in, how efficient are we moving, are we faster compared to other surgeons, are we relatively slow. So we want to make a sort of benchmarking possible, as well as an international comparison. Like I said, robotic surgery, I think it's just the next step towards digital surgery. We're always looking to improve and always looking to further enhance the outcomes of our patients. We're doing so with robotics, machine learning, improving instruments, and our 3D visualization. I think that's the most important part of our presentation. We're still working. We're doing the best we can to always keep improving. I've taught you about minimally invasive surgery, the introduction of robotic surgery. I've shown you some results, identifying the safety and how expensive it may be. I've taught you that perhaps we might be able to have fewer patients receive a permanent stoma when we perform the surgery robot assisted, and that we're still working towards digital surgery. Thank you.
Thank you so much. Very inspiring, and that's all happening here. Cool. Any questions from the audience? Yeah. We have the catch box.
Yeah, thanks for the nice presentation. I was wondering, because you're working with a robot to perform the surgery while looking into a digital screen. Could you use that as well to train your surgeons in VR?
Yeah. So we're already doing so. So for instance, the Da Vinci robot, it already has several simulations in which it starts relatively simple. You have to pick up something and displace it to another place. And it can also teach you how to do simple sutures, etc. That's all in a simulated model. It's sort of like we have it's simulated. So there's no patient involved, but there are some models where you have a sort of like anatomical black box in which the instruments are hidden, and then you can perform the surgery in there. And then it tells you how efficient you are, somewhat similar to what we're doing for the face detection. So we're already training on the simulation models. And if we're able to develop all of these new features, of course, we want to introduce these into the simulation models also. So we're already in very close contact with Da Vinci, because the industry is actually helping us a lot in all these projects, because they know how their product works, what would be feasible, what would not be feasible. So we're working with various partners.
And accompanying that question, is that training also being recorded? Like you could probably use it as also training input to create an automated surgery robot as well, especially when you're looking for finding the points that are relevant within such a surgery. So I don't know.
Yeah, so we're still quite far away from doing that like autonomously by the robot. We are slowly trying to give some more tasks to the robot, but as we said, it's very difficult because the robot is not used to changing circumstances. So where a surgeon is able to identify a bleed and identify that it needs to be stopped right now, or there's a different anatomy as a patient has maybe received neoadjuvant chemoradiation therapy or has had previous cesarean section, then the anatomy of the pelvis might be different, and the robot does not recognize that at all at the moment. Yeah. So it might be feasible on a very generic standard patient. Yeah.
There probably isn't one.
Not yet.
But virtual training is a great cause because we're operating less and less in our training, so it's a great way to enhance your skills. Any other questions? Yeah.
I think you made a very good point in looking at the cost. For example, I also always wonder, should we look at the cost at the moment, how much a robot costs to the department or clinic, or the long-term effects, of course. And fevers, permanent stomas is a very, very good measure already because you can put it in numbers. But I'm wondering, perhaps the actual model is much more complex than that, the recovery time of the patient. And then you mentioned the back pain of surgeons, which is very important because if a surgeon is out because of health problems, that also costs in everything, quality of care and everything. So I was just wondering, are you guys looking into more complex models to create both long-term and short-term cost, and also in a much bigger context?
Yeah, so for the short-term cost analysis, we've looked at the cost at 30 days post-operatively, and to sort of assess cost, we've looked at the cost of the hospitalization period, the surgery itself, including the payments of the anesthesiologist, the assistant, and the instruments. And we also looked at the following the discharge at complications, readmissions, and reinterventions, which was up until 30 days, and it was limited, but it was our first best effort at providing some insight into costs. For the long-term assessment, we're also introducing a cost of, for instance, a stoma. Like I said, there's material cost, but there's also stoma reversals, stoma revisions, which can be quite costly because they need another surgery. So we're already trying to expand what we're taking into the cost comparison. And for the Advantage trial, we hope to have the first results by the end of 2024. And we're sending patients questionnaires, which also assesses their workability, loss of productivity, and etc. Because that simply hasn't been looked at all. Yeah.
But it's not the same payer.
Sorry?
It's not the same payer. So if the patient goes back to work earlier or misses last days, it's not the same payer as the insurer that pays for the robot here in the hospital. Can you account for that at all? Is that possible? It's very challenging, I understand.
Yeah, so what we're trying to do is we're trying to provide a sort of total cost overview, which indeed it comes from the pockets of different individuals. Our short-term and long-term retrospective analysis will be mostly focused on from a health insurance perspective. And then for the Vantage trial, we want to look at a societal perspective. It's called in economic terms. And including in the societal aspects are all also loss of quality of life. You can actually, the quality adjusted life years, you can also put a price on how much we as a society are willing to pay for a human being to have 1 year in good health. We're also looking to see how much having, for instance, a stoma and reintervention, readmission will affect one's health, one's quality of life, and to see if we can also put that in numbers, which is, I think, interesting for the future.
Thanks. We have a question over there. Please throw it up.
I'll try.
Just a intermediate question from a medical legal perspective, legislation. The recordings of a robotic surgery is sort of a black box, or it's actually a visual box, I guess. When something goes wrong, is it put into trial, and can you look back what happened, and does that play a role at all? Is that part of a surgeon may get scared that everything is recorded now?
Yeah, I'm not sure. I haven't had the pleasure of making a mistake, being recorded, sued, and everything. But no, I suppose it should be used to even to potentially evaluate the surgeon, and then of course you want to evaluate him as opposed to his peers. To see, you don't have to be a superhuman surgeon. You have to be non-negligent for the judge to assess whether a medical error was your fault or not. I think so. I suppose it will be used. It might be used, but I'm not entirely sure. Yeah.
Somebody's really looking at your fingers, literally, right? Please go ahead.
Hello, Jeroen Gleijs, AI Hub Noord-Nederland. I have a question for the insurance company. There have been some questions already. You have all these different cost calculations. You have just the operation, but then you have the follow-up cost for the savings on the stoma, and then you have additional savings on being able to work better or longer or have less absence to work. Up to what point do the insurance companies accept any cost calculations?
As soon as you leave the hospital, it's kind of over, I guess. Mostly it's focused, I believe, on the healthcare perspective from the insurance companies. So everything that they pay for is of their interest. And then, like I said, for instance, the quality adjusted life years, we as a society have said in the Netherlands, we're willing to pay around 50,000 euros for 1 year in good health. So if it turns out that we're able to provide people with a longer time of acceptable health, then we need to also adhere to the consequences that we will pay more for that. But who exactly is going to pay that and how? That's a good question.
Yes, reallocation of budget, that is the thing.
Yeah, no, I understand, but I think this is the next step towards, we've looked at the oncological safety of robotic surgery and we found that it was at least equal and perhaps the post-operative outcomes were better. And I think the next step we should be taking and asking ourselves is how much more does it cost, if it costs more, and how much are we willing to pay for that, knowing that you might have a, for instance, smaller chance at receiving a stoma.
Do insurance companies incorporate the stoma issue? Or is it just operation?
Yeah, so in the hospitals we have like a package that's being paid for a certain type of surgery. And for instance, for the reversal or revision of a stoma, there's a package, a couple €1,000 for the revision surgery and 3 or 4 days of admission, which is based on average costs. So it is, I think, accounted for, but these costs are not made public, at least not to me. And they also, as far as other journals go, we found very little studies actually implementing, for instance, stoma costs and loss of productivity in their cost evaluation.
Okay. Thank you.
We have one final question, and then we'll move on to Gloria's final demonstration.
Okay, so thanks. So I was thinking about the things that you've checked for, so cost and safety, and I was thinking as a patient, so when would you be able to trust these systems? And one of the things I would be interested, well, that would worry me with surgeons looking at their screens and operating is that they might be missing cues from the environment that would otherwise be picked up. Maybe the feedback from the patients or the lack of feedback from the patient. Mm-hmm. So isn't that something that, so maybe that isn't relevant in practice, so I don't know how, I don't know anything about this, how this is being, so how this works in practice, or maybe there is some connection, but is this something that you're worrying about, thinking about, or?
Well, so in the it's a difficult question that I don't have a straightforward answer to. I think in the operating room, there's always different people looking at looking after the patient. For instance, the anesthesiologist will look at, perfusion, saturation, etc. Regarding some cues that we might not see, our visualization with the robot is better than we've achieved with laparoscopic surgery, and perhaps far better than we are able to achieve using open surgery, particularly when there's a trainee surgeon. In open surgery, often the supervising surgeon won't have the same field of view because you can't both look down towards the patient. So our visualization might actually be better. Small cues such as the patient somewhat having more active muscle contractions or something. There's always at least 2 OR assistants at the patient's side because they have to replace and readjust the arms if needed, and often also a surgical trainee. I won't be able to say if we miss cues due to that, but at least the large ones, the bleeds, etc., we should be able to see even better. Yeah.
Okay, thanks.
Final question. There's a box left on your left.
I have very silly question, please. So when I look this picture, it's very common. Why do such robots has 4 fingers? I mean, maybe 3 fingers or 5 fingers can be more efficient. I mean, only because we human have 4 fingers. Is that reason? Or, I mean, I just can't imagine. It doesn't have to be exactly the same as we have, right? It doesn't, right? I mean, the surgical, at least the robotic assisted surgery, do they always have 4 fingers and thumb? Like?
Not that I'm aware of. No.
Okay.
I think it's it might just be the way it's depicted because it's easier. I don't know.
Okay.
But
God only knows, right?
Yeah.
I think you should end with a slide, those intraoperative pictures. Thanks so much.
Thank you.
Gloria, the floor is yours, or your robots. Thanks, Ritch. It was very inspiring, and thanks so much for being here.
Hi, everyone. Welcome to our demo. My name is Robin. And I am Sam. We are the 2 robots of the Aurora group. Yes, like on our t-shirts. We work with researchers and clinicians at the ENT department in the UMCG. That is right. We help them run some tests with children and adults. My favorite part is that we get to meet lots of people and make new friends. What do you like the most, Robin? I like all the traveling. We have visited some schools, museums, and clinics. Yes, that is also nice. Anyway, shall we show them an example of what we do, Robin? Yes, Sam. Let's do it. I will run 2 tests and you can be my participant. Okay, I am ready. For the first one, I will say some words and you have to repeat them to me. I will evaluate if you got them correct or not. All right, let's begin.
Bus.
Bus.
Pen.
Pen.
Lip.
Lip. Well done. Thank you. That was pretty easy. Okay, shall we move to something more challenging then? If it gets too difficult, can our audience help? Yes. I will now say 3 numbers while playing some background noise. You have to pay attention to the numbers and repeat them to me. Are you all ready?
It's in Dutch, by the way.
Oh boy, I have no idea. What digits did Robin say? Can anybody help me? 3. 5.
And?
2. 4. 6. 3. 5. 2. 9. Jeez, that was hard. Yes, it can be difficult at times. But it is necessary to test your hearing. Oh, after all this testing, I think I need a rest. I agree, me too. Thank you for coming, you guys. Hope to see you soon again. If you have any questions, please ask our fellow humans. Bye.
All right, that concludes our session. Thanks so much for coming. And the Femke, thank you much for organizing. Round of applause for Femke and organizing this jazz. Oh, she's back.
Yes, I'm there. Yes, I would like to thank all speakers and Job for the chairman of the day. Applause for Job also.
Of course.
Thank you so much. Well, I only have one, but it's for your whole team. Thank you so much. And of course, Job.
Oh, really?
Yes, also.
I will give him right back to you because you deserve them. Here. Cheers. Thank you so much. And the drinks are outside there on the left side, Femke? Yeah? So right behind that door, there are drinks for the bowl and further discussion. Thanks so much for coming. And to our speakers, of course, Ritch and Hamid and Gloria.